Well, we have, all we need really, if we compute these partial derivatives, then we're all set. If all we have is this, how can we get the partial z with respect to x and y? As we discussed earlier today.
Want to do a replay?
Would you negative partial of x over partial z?
Yes. So minus partial effect to x, z. So we could get them this way. Fy over fz. Don't feel bad. My upper level, my graduate class this morning, they couldn't remember something from 5 minutes before. Of course, that was an 8 o'clock class. Which, by the way, I will have in the summer and in the fall. I'm so thrilled. And it's 167.
At least it's over fast.
Yep. So we could do this. But what's the one potential problem with this approach?
Z is 0.
Yeah, that z is 0. That doesn't mean there's not a tangent plane. There still is one, but we just can't compute it in this way. So we need to junk this approach and come up with something better. So here's what we can do. We can try to reason about this geometrically. So any curve called C contained in the surface f of x, y, z is equal to 0 is also a level curve. Of f. And that's what we're going to use to help us here. Because it's a level curve of f, that means that if here, this is our surface, here's a particular point on surface, here's a tangent plane we're trying to get, and we have some curve that's passing through this point, so x naught, y naught, c naught. So curve passes through this point, then its tangent vector so the tangent vector of this curve at this point is in the tangent plane. So we could draw curves through this point going in any direction. So any direction within a tangent plane you can think of as a tangent vector. So you give a tangent plane as a collection of possible tangent vectors of curves that pass through this point, and very important, curves that belong to the surface. Because you can think of this surface as a collection of infinitely many curves, if you like. So this point here, this curve that I'm drawing here is a level curve of your function f. So this vector, this tangent vector here, how does it relate to the gradient? Because this tangent vector is a direction of a level curve. So how does it relate to the gradient of f? As we discussed earlier today.
It's more than 5 minutes ago, right?
Yeah.
I get the rewind function and figure out on this camera.
So let's go back to this picture here. So here we have a curve. FML, I just gave it away. Anyway. Well, by going to this picture. All right. This is the direction of a level curve. How does it relate to the gradient?
It's perpendicular.
Yes, it's perpendicular or orthogonal. So what that means is any direction in the tangent plane is orthogonal, perpendicular to the gradient of f. So So the gradient is the normal vector of the tangent plane. Okay. So because we're dealing with a level surface full of level curves passing through this point, this gradient vector, since it's orthogonal to level curves, must be orthogonal to every direction in the tangent plane. It's orthogonal to the entire plane. So it's the normal of a plane, and as I hope someone remembers from 169, that if the gradient of f at this point has these components, A, B, and C, what is the equation of a plane? All right, some of you should so know this.
A plus BY plus CZ.
Yeah, essentially.